Hi, this is Sudeep and I welcome you back to this wonderful series of learning structure analysis with StatPro. If you are new to this channel, you are welcome. Please do consider subscribing to this channel and do hit the bell icon for more notifications from this channel. So in the last session, we discussed about the parallel axis theorem and how we could calculate the moment of inertia of composite section using the parallel axis theorem. We even saw how we could roughly calculate the moment of inertia of an I section. Now in this section, we will solve two detailed problems with the parallel axis theorem to make the concepts more clear. But before we go into that, we had one essential thing to discuss, and that is about the units of moment of inertia. Now we know that the moment of inertia is given by this expression. It is given as the second moment of the summation of the second moments of all the component areas about the axis of interest. Now this is an infinitesimal area, or this has the units of area, which would be the length would be given, or the units would be given as length square, right? So because area has the units of area would be length square, and this one is y, which is the distance. So here the units would be lengths, but since it's squared, the units of this two, y square, would be l square. So finally the total area would come as length to the power 4 for the moment of inertia. So the units thus would be length units to the power 4. So the units that we would see for moment of inertia would be something like millimeter to the power 4, meter to the power 4, inch to the power 4, and so on. So length units to the power 4 is the unit of moment of inertia. So unit of moment of inertia. So let us do a quick recap of the parallel axis theorem. So let this be a cross-sectional area of a general shape. It can be any possible shape, and let this point be the centroid of the whole cross-section, this point C. Now we want to find out, so let there be a partial area. Let us identify a partial area A within this whole cross section, and we are interested to find out the contribution of moment of inertia of this area about this axis and this axis. Okay, we have a horizontal centroidal axis and we have a vertical centroidal axis, and we are interested to find out the moment of inertia contribution from this particular area about this axis and this axis. So is this clear? I hope. Now let this be the centroid. Let us write the area here. Now let this be the centroid of this partial area that we have identified, and let this be the centroidal axis of the partial area, okay, and which is parallel to the axis system, or the centroidal axis system of the whole cross-sectional area. So this is parallel to this and this is parallel to this. Let us call this as z dash and let us call this as y dash, another axis system. Now let the distance between these two parallel centroidal axes y dash and y be given by z, and let the distance between these two parallel axes z dash and z is given by y. So this is z because we are measuring along z, and this is y because we are measuring along y. Now as per the parallel axis theorem, the contribution from this area the contribution from this area. So if we want to find out the contribution of this area to the moment of inertia of the whole cross section about the z-axis, we have to write that as Iz. It would be given as the moment of inertia of this partial area about its own centroidal axis z dash plus the area A and the square of the distance between these two axes, so ay square. Similarly, if you want to find out the contribution of this particular partial area to the moment of inertia about the y-axis, which is given by Iy, it will be Iy dash. So the moment of inertia of this partial area about its own centroidal vertical axis plus the area into the distance between the two, the square of the distance between the two axes. So it would be given by this. Now these are from, this is what the parallel axis theorem says. Okay. Now we will use this parallel axis theorem to solve a couple of problems. Now in the last session we have spoken about the section bending in the plane of symmetry. I just want to emphasize on the fact that the parallel axis theorem is valid for any general cross section shape as well. Only the axis needs to be chosen through this to pass through the centroid of the whole cross section because of a requirement that we will discuss when we talk about the flexural theory of beams. Also, in general, this expression I equal to integration of y squared dA is valid for all shapes of cross section and does not need to be a cross section which bends in the plane of symmetry. So like the moment of this expression of moment of inertia and the parallel axis theorem is valid for any shape of the cross section. Alright, so now we will solve our first problem using the parallel axis theorem. So I have taken this problem from this book, Strength and Elasticity of Structural Members by R.J. Oates, and this is the section that we want to find the moment of inertia about its horizontal centroidal axis. Now let me try and explain a bit about the section first. So in this is an I section, as you can see. The top flange is 3 inches. So we are doing this in English units and we will solve another problem in the metric units after this. So yeah, now getting back to explaining the section. So the top flange here is 3 inches wide and 1 inch thick. The web here is 8 inch in depth, or that is from the bottom of the top flange to the top of the bottom flange, the depth is 8 inch and the thickness is 1 inch. The bottom flange, that is 9 inches wide and 1 inch in thickness. Okay, now we want to find out the centroidal, the moment of inertia of this section about the horizontal centroidal axis. Now, the first thing that we need to identify is the centroid of this particular section. Now, see, it wasn't very difficult to identify the vertical centroidal axis because we knew that it was the plane of symmetry, it was the axis of symmetry which would divide this section into 2 equal and similar halves, so it wasn't difficult in identifying that. But to locate the horizontal centroidal axis, because about the horizontal axis, as we can see that the beam is not symmetric. So in order to identify the horizontal centroidal axis, we need to do some calculations. Okay, now the first thing that we want to do here is, okay, now let me explain these dimensions in red. Now each of these components of this section, that is the top flange, the web and the bottom flange, we have found out the centroid of the individual the area of the individual components. So the centroid of the area of the top flange, so top flange area is 3 inch into 1 inch, so 3 inch square. That's a rectangular section, and this centroid would lie here at the center. So we have identified the distance of the centroid of the top flange from the bottom flange. So if this is 0.5, so this one is 1 inch deep. So from here to here, right, from the centroid to the bottom of the top flange, it will be 0.5 inches plus 8, which would be 8.5 plus 1 inch. So it will be 9.5. So 9.5 inches from the centroid of the top flange to the bottom of the bottom flange. Why are we identifying this? Well, we'll see in a moment. Now, let us identify the centroid, the distance of the centroid of the area of the web from the bottom of the bottom flange. Now, we know that again, this is a rectangle, so its depth is 8 inches. So the centroid would be at half of this distance. So it is at 4 inches from the top of the bottom flange. So it is 4 inches plus 1 inches would give 5 inches. And similarly, for the bottom, the centroid of the area of the bottom flange, the distance of this centroid from the bottom of the bottom flange is 0.5 inches. Okay. Now with all this information, we intend to calculate, or we intend to find out the distance of the centroid from the bottom of the bottom flange, or we need to identify the location of the centroid. Okay, so what are the components? Let me write this comp, which would mean components. So the first component is, let us say, we'll start with the bottom flange. So we'll say bottom flange. Then the second component of this section is the web, and the third component of this section is the top flange, which will be top flange. Okay, now the next thing that we need to do is to calculate the cross-sectional areas of each of these components. What is the cross-sectional area of the bottom flange? 9 inch wide, 1 inch in thickness. It's a rectangular cross-section. The bottom flange is a rectangular cross-section. So the area would be 9 inch into 1 inch, right? So that would be 9 inch square. So that is the area of the bottom flange. What would be the area of the web? Well, 8 inches in depth and 1 inches in thickness. This is again a rectangular section. So 8 into 1 would give 8 square inches. And what is the area of the top flange? Well, 3 inches wide, 1 inch in thickness. So 3 into 1, 3 inch square inches would be the area of the top flange. Now, let us indicate the distance of the centroid of each of these areas of the components from the bottom of the bottom flange using this expression y bar, which is in inches. So for the centroid of the bottom flange from the bottom of the bottom flange is, the distance is 0.5 inches. For the web, as we have seen, it's 5 inches. And for the top flange, the distance of the centroid from the bottom of the bottom flange, the distance of the centroid of the top flange from the bottom of the bottom flange is 9.5 inches. Okay. Now, what is the total area of this cross section? Well, the total area of the cross section would be nothing but the summation of each of these areas. So the summation of each of these areas would be given by 9 plus 8 is 17, 17 plus 3 is 20 square inches, right? It would be 20 square inches. The next thing that we need to find out is the distance, it would be the product of the area of each of the components with the distance of the centroid of the individual areas from the bottom of the bottom flange. So that would come as, now this is A into y bar. The units would be in cubic inch. Why? Because the cross-sectional area is in square inch and the distance of the centroid of the components, the area of the components from the bottom of the bottom flange is in inch. So inch square multiplied by inch would give the units in cubic inch. So what would be the product of this and this? It would be 4.5 cubic inch. For the web it would be 40 cubic inch, and for the top flange it would be 9.5 into 3 would be 28.5 cubic inch. Okay, now so what is the summation of these values? The summation of these values, 5 plus 5 would be 10, so it's 0, it is 73. Okay, now there is an important principle that you need to know. If the summation of the individual areas multiplied by the distance, so the summation of the products of all the individual areas multiplied by the respective distance from any point will be the product of the total area into the distance of the centroid from that same point. So basically then, to calculate the distance of the centroid of this whole area from the bottom of the bottom flange, we need to calculate this as, so this would give, so let that value be y, so this would be given by summation of ay bar by summation of a, right? So basically what it means is, let me explain that again. So the area into the components of each of the component should be equal to, this is a principle, this is a theory, that this would be equal to the total area of the cross section multiplied by the distance of the centroid from the same point, right? So basically if we express that and just try and find out this value, which would be the value of the distance of the centroid from the bottom of the bottom flange, you will get this expression. So then it would be 73 inch cube by 20 inch square, so it will be 3.65 inch. So that means that the centroid of this cross-sectional area is located at a distance of 3.65 inch from the bottom of the bottom flange. So thus we have identified the location of the centroid of the area, and we have identified the horizontal centroidal z-axis, which is at a distance of 3.65 inches from the bottom of the bottom flange. So our first work is done. We have identified the location of the centroid. So now we have to calculate the moment of inertia of each of the individual components about its own centroidal axis. So for the bottom flange, this and that, remember that centroidal axis. Now we are intending to find out the moment of inertia of this of the whole cross section about this horizontal cross section. So the centroidal axis that we'll choose for each of the individual components has to be parallel to this particular axis as per the parallel axis theorem. So what would be then, so these are the individual axes that we would be working on. So basically we'll find out the moment of inertia of the bottom flange about this cross section. So that would be nothing but BD cube by 12 because it's a rectangle, right? So 9 into 1 cube by 12, and 9 into 1 cube by 12 would mean that, let me take this calculator, so it would be 9 by 12 would be 0.75 square inch. So we are finding out what? The moment of inertia. So the individual moment of inertia of the components about their own centroidal axis, and for the bottom flange that is 0.75. And this would be, remember, what would be the unit of this? I had discussed this in this video. So that would be inch to the power 4. The moment of inertia values are given in the length units to the power 4. The next, the moment of inertia. So we'll identify the next, for this web, we want to find out this would be the horizontal centroidal axis parallel to the z-axis for this web. And what would be the moment of inertia of this about its moment of inertia of the web about its own centroidal axis? It would be 1 into, the depth is 8, right? So 1 into 8 cube by 12. So that would come as 8 cube is, so 8 cube by 12 would come as 42.67. So we have 42.67 inch to the power 4. And finally, for the top flange, its own centroidal axis is this, right? This is the centroidal axis of the top flange, its own centroidal axis. So then the moment of inertia should be 3 into 1 cube by 12. So that would be 3 by 12, which is equal to 0.25. Right. So we have found out all the moment of inertia of the individual components about their own centroidal axis. But that doesn't solve the problem. We have to find out how these components contribute to the moment of inertia of the whole cross section, and that would be given by the parallel axis theorem. So what we now need to find out is the distance of this particular CG from all their individual centroidal axis, right? So basically then this distance would be what? This distance would be, so this is 3.65 inch from here, so minus is 0.5. So minus 0.5 will give the distance between this axis and this axis. That is what we intend to find. So this axis and this axis. So that would be 3.65 inch minus 0.5 inch. So this would be 3.15 inch. For the bottom flange, that is, let us calculate this as distance. So this distance would be 3.15 inch, right? And then what would be the distance between the centroid of the web and the centroid of the whole section? Well, this is 5 inch and this is 3.65 inch. So if we subtract that, if we subtract 3.65 from 5, we will get the value or the distance of the centroid of the web from the centroid of the whole cross section. So that would be 1.35 inch. So 1.35 inch. And finally, for the top flange, what's the centroidal distance from the bottom flange? 9.5. And so 9.5 minus 3.65 would give this distance. So what would be that value? 9.5 minus 3.65 would give 5.85 inches. Okay, Now, finally, what we'll now need to do is to, now remember the parallel axis theorem, how this works. So the contribution of each of these components to the whole moment of inertia of the whole section would be given by the individual components plus A into d square. So here we find out the I contribution, right? And remember that this would be given by that I contribution of each component would be given by the moment of inertia of the individual component plus A into d square. So what would be the I of this component? 0.75, right? This is I of this component is 0.75 plus A is 9. So 9 into what is D? 3.15. That we have to square that. So the value would come out as 90.05 inch to the power 4. What would be the distance for the web? The distance from the web is same thing. So the moment of inertia of the component is 42.67. So we add that with A into d square. What is A? For this, A is 8 into what is D? D is 1.35. So 1.35 square. That is 57.25 inch to the power 4. Finally, for the top flange, we have the moment of inertia of the individual component is 0.25. So this is 0.25 plus the area is 3 into d square. So that is 5.85 whole square. So that would give the value as 102.92 inch to the power 4. So now the total moment of inertia of this cross section of about the z-axis of the whole cross section, the moment of inertia of the whole cross section, I would be given by the summation of I contribution, right? The contribution from each of the components, and that would be equal to the summation of all these values. So it would be equal to summation of all these values. So what do we get? 90.05 plus 57.25 plus 102.92. If we add them all up, we get 250.22 inch to the power 4. So what is our moment of inertia of this whole cross section about the z-axis, the horizontal centroidal axis? It is I equal to 250.22 inch to the power 4. So now we solve our second problem, and last problem that we had solved was in English units. However, this is in the metric units. All dimensions are in millimeters, and we have taken this problem from the book Engineering Mechanics of Solid by Igor P. Popov. So we have this section. Now let me explain a bit about this section here. So we have a hollow section here. It's a rectangular section overall, but it has a rectangular hollow in between with the dimensions given as appropriate. So this one would be 20. So basically then the hollow dimension is 20 millimeters by 30 millimeters, while the overall rectangle is of 40 by 60 millimeters in dimensions. Now, one of the things that we definitely can do is we take each individual components like we had in the last time and find out the moment of inertia about its individual centroidal axis and transferred them to the overall centroidal axis of the whole cross section using the parallel axis theorem. But so in that case we had to take 4 components, 1, 2, 3 and 4. But here what we'll do is we will take a far easier approach. Okay, and what we'll do is we will consider 2 sections. One is we'll consider a positive section, which is this whole rectangular section, and for this hollow section which doesn't have anything, right, there is no material in it, it's a hollow, so that we'll consider as a negative area. Okay, so for member here we write full section, which is the full rectangular section, and then we have the hollow section. So the hollow section would have a negative area. So the area in millimeter square, we can express this as, so this one would be what? For the full section, right? Just imagine it's a full rectangle of 40 millimeters by 60 millimeters. So 60 into 40, 2400 millimeters square. And for the hollow section, it is 20 millimeters by 30 millimeters. So 30 into 20 is 600. So 600 millimeters square, but it's not, it doesn't have any material in it. So it's a negative section. So we put that as negative. And like we did in the last time, we find out the summation of the whole cross-sectional area by adding these 2 up. So if we add these 2 up, it would be 2400 minus 600. So it would be 1800 millimeters square. The next thing that we want to find out is about these 2 areas is the distance from the lowest part of the bottom flange, which is it. Remember that here again the intention is to find out the moment of inertia about the horizontal centroidal axis. So we are trying to find out the location of the centroid in the first place. Now again, like in the last problem, we are trying to find out the centroidal axis with reference to the bottommost portion of this rectangular section. So what would be the distance of the CG? So we'll give it as again y bar in millimeters, and the distance of the CG of the whole rectangular section would be 30 millimeters. So it would be half of 60 millimeters. So it would be located 30 millimeters, right, above the bottommost portion of this section. And for this hollow section, it would be at half of this 30 millimeters. So it would be from the bottom of the hollow section to the centroid of the hollow section, it would be 15 millimeters plus 20. So 20 plus 15 would give 35 millimeters. The next thing that we want to do is A into y bar, which would be in millimeter cube this time, and 2400 into 30, if you do, it will come at as 72 into millimeter cube. And for this negative area, since this area is negative, multiplied by this would come to around okay. So like in last time, the centroid would be found out, the distance, let the distance of the centroid, let the centroid be located here, okay, and this is the horizontal centroidal axis. So this is the Z, okay. Now what would be the distance? The distance would be y from the bottommost part. So y would be given as, like last time, it will be given as summation of ay bar by summation of a. Now we haven't done the summation of ay bar, so it would be ay bar would be equal to add this 2 up, 70, these are 10 cubes, so it remains common. 72 minus 21 would be 51. So it is 51 into 10 cube millimeter cube. So now we can do that, this one as 51 into 10 cube millimeter cube divided by A is 1800 millimeter square, and if we solve this using my calculator, then this would come to 51 into 1000 by 1800. This comes as 28.33 millimeters, right? So then this distance here would be 28.33 millimeters. Now, now that we have found out this, what we do, the next thing we want to do is we want to find out the moment of inertia of the individual components. So for the whole rectangular section, it will be BD cube by 12. So 40 into 60 cube by 12. So what we'll get, it is, we'll get this as 40 into 60 to the power 3 by 12. I'm using my calculator for this. So we get, this one would be millimeter to the, we are using millimeter unit, right? So millimeter to the power 4. So this comes as 720 into 10 cube millimeter to the power 4. Now the moment of inertia of this hollow section, it's a hollow section, so it would be minus. So it would be minus and then BD cube by 12, 20 into 30 cube by 12, right? So this one is 30. So 20 into 30 cube by 12, that comes as 20 into 30 to the power 3 divided by 12, that comes as 45. 10 cube, right? So these are the moment of inertia of the individual components. Now let us calculate the value of D in millimeters, right? The value of D would be calculated as the distance of the centroid, right, of the individual components from the centroid of the whole cross section. So this one is at 30 millimeters, right? 60 by 2 from the bottom flange, it would be 30 millimeters for this whole section. So that minus 28.33, the distance would come out 30 minus 28.33 is equal to 1.67 millimeters. And this one, for this would come as 30 by 2, that is 15 plus 20, 35. 35 minus 28.3 would come as 28.33 would come as 6.67 millimeters, right? So now we need to find out the inertial contribution of these individual components. So now we want to calculate the contribution of the moment of inertia of all these individual components. So what we'll do, it would be I component plus A into D square. So the I component for this is 720. So it would be 720 into 10 cube, right? Plus, what is the area here? The area is 2400 into what is D? 1.67. So 1.67 squared would come out as a big number. If I divide that by 1000, say, then that comes out to be 726.7. I have divided that by 1000, so it would be 10 cube millimeter to the power 4. Now for this, it would be again a negative value. So individual contribution 45 that it actually doesn't add, it actually takes away, right? So that's why minus 45. So individual contribution 45 into 1000 plus, 45 into 1000 plus the area is 600. So 600 into the value D is 6.67. So 6.67 whole square, that comes out as 71,693. So if I divide that by 1000, it comes as 71.7. 71. So it would be minus, since it's a hollow section, 71.7 into 10 cube millimeter 4. So what would be the total I? What would be the IZ of this whole cross section? The IZ of this whole cross section, or the total I, would be IZ, moment of inertia about the Z axis of this whole cross section, would be the summation. This is not the summation, sorry. So IZ is the moment of inertia of this whole cross section about the Z axis. It will be the summation of these two. 10 cube is common, so 726.7 minus 71.7 gives 655. So 655 into 10 cube millimeter 4. So we found out that therefore the required value, therefore the required, or the moment of inertia of the whole cross section about Z axis is equal to 655 into 10 to the power 3 millimeter to the power 4. So this is our required moment of inertia. I hope the two solved problems would have dispelled whatever doubts you had on the parallel axis theorem. If not, please ask your questions in the comment sections below. And if you think that I have added value in this session, please do hit the like button so that it reaches out to many more students across the world, giving worth to my effort. Thank you for being with me. See you in the next session. Till then, bye.